Okay, I'm ready to get started. Hopefully don't blow my microphone out of the water, which leads to bad recording, but I got too many things to check out every time I get back from class and say, I'd like to make that better, and then I go off and get going on something else. So in terms of what I've posted up new on the website, the only thing I've really done is I put up the solutions to set 3, because I'm really bogged down with grading for my other DSP class, which they took an in-class exam, and there's a lot more people in there, and there's a lot more papers to grade, and I'm way behind. So I've been focusing on that besides their project. But I did repost also the take-home exam sheet, fixed a few typo errors, and then I took and got rid of the point count, which was incorrect. So we're going to get back into pulse shaping, and then we'll move off into other things like eventually into fading and then equalizers, hopefully today. What I want to do is start the day by just seeing if there's any questions you have on the take-home exam. I've done some more things myself because I've got different problems on here than I did before, so I'm also working at least one new problem. It's fair, right? Unfortunately, it's time-consuming. So now for the questions.
Yeah, I had one question. I think it was problem 3. It was the one about cable loss.
Yeah.
As I understand, N0 is the noise level of the receiver, right? So
Yeah.
N0 doesn't have any cable loss. It's just static, correct? Or it's at that one level, right?
That's right.
Okay.
It's the signal that's going to endure a loss going over the cable to get to that N0 point.
Right, okay.
So let me just take a quick look at my solution.
That's what
Yeah, so the way I did the problem is I wrote down loss in the cable as being equal to, because it's going to be a dB value, right? You're looking for an attenuation. So I said it's going to be equal to EB over N naught at the transmitter in dB minus EB over N naught at the receiver in dB that achieves the 10 to the minus 9th error probability. Does that make sense to you? The difference between those two dB values is going to be the cable loss. The only tricky thing to figure out is you also have to go in and figure out what is EB at the transmit side, and that's assuming that it's driving into a 50 ohm system. So you have to go through the conversion from watts into 50 ohms with the voltage given, and then convert that, say, to dBm, because you'll probably be using the minus 170, or let's see, no, you're going to be using the minus 160 dBm per hertz N0 value. So I'm just thinking of when I've used this problem before, you've got to convert. So the biggest thing there is that power, we're so used to in signals and systems just being, say, the amplitude squared divided by 1 if it's a 1 ohm system, but now it's a 50 ohm system, so we just have to replace 1 with 50 to get that value to come out right. Is that good with that?
Mm-hmm.
It's in this problem because I think it's just something that you need to do, because it's just, if you're a systems analyst engineer and you're going to talk to the test engineer that's getting ready for an acceptance test or whatever, and they've got the test equipment, it's in a 50 ohm environment, and they say, well, I'm going to set up my test like so-and-so, an N0 noise source or something like that, and then you want to guide them to get the right setting. And I've certainly been there Well, I did everything in my, this was like the beginning of my career. I was working in the lab, I was doing some modeling, and then I was designing circuits and doing boards, all that stuff, but something that always came down at the end of virtually every system that was delivered was a bit error rate test, or probability of bit error test in front of the customer, where you demonstrate to them, here's my signal power, here's my noise power in density displayed on some instruments, and then you have the numerical error count value from the or from the experiment, and there's a checkbox or something on the acceptance test. So you want to make sure it's calibrated right. Any other questions?
I have a question about the last problem.
Okay.
And my question is about how I have a problem in the implementation of the filter.
Okay.
And because I don't know how I should implement Butterworth filter in Python.
Okay.
Because in this question, I think we have a numerator and denominator. And,
Okay. I don't think there's a Butterworth filter in there. There's just the first order filter, right?
yes.
But I'm glad you asked the question because I got ready. There's actually a simulation example in the notebook that there's some things I wanted to show, and that may help also explain that too. So
Yes.
I'll go take a look at that right now.
Yeah.
And for my table of contents for data transmission and noise, I can just go down here and I can see, here it is, a simple simulation case study. So in this case study, I did use a Butterworth filter. I used a third order Butterworth filter, and I wrote this top level simulation function just patterned after, I'm going to explain this a little bit more just so you can see what you can do. I patterned it after the binary PSK area where I defined PSK simply as this, and then I defined my PSK simulation function like this, and this one uses as one of its inputs, well, never mind. This one gets the matched filter, which we were using in this simple simulation, as a rectangle, which is right here. And then the received signal, after it has noise added to it and was generated with the PSK function, it gets added to it, and then I pick the right timing instant, and I'm going to go through that here in a second. And then I go ahead and call those other couple of functions to get the error probability measurement, okay? So I took this function right here and I copied it, I believe, and that became a variant of what we were just looking at. That became this, and this essentially is already almost your problem, because what I did is I just commented out the rectangle matched filter. I put in a Butterworth of order 3, and I gave it a cutoff frequency in terms of the bit period, and then I have to divide by NS, the number of samples per bit. So this is a parameter that goes into the system. So it says, I'm confused, yeah, it's the second parameter that goes into the system. And then I went ahead and did everything else, and I don't know what's on the website, but apparently the last time I used this notebook, I also decided to put in the simple filter that this problem involves. This would be the equivalent filter coefficients right there. 1 minus A for the numerator, single coefficient, that just makes the gain unity at DC. And then 1 comma minus A, and then parameter values. And then I added, just for convenience, I added another input argument into my function so I could turn knobs on that remotely. I'm not going to demonstrate that because that's what you're doing in that problem, but I will demonstrate this function with the original Butterworth So it's been loaded, and here is the time bandwidth product. And right now in this function call, that variable at the end is doing nothing. That would be the parameter for the filter that you're studying. But I wanted to just point out a couple of things in here. So what this function does, remember, you can always go Shift-Tab, and you can see the doc string that I wrote. So theta is a static phase error for demodulation. We're not using that in this example. It was used earlier. The number of bits is fixed. I think I probably said fix it at 16. So that's been fixed. Well, I guess that's coded internally. And then the number of bits to run, in this case it was 1,000. You're going to have to run more. I want to talk a little bit about this timing value, though. This is the timing value that nominally has to be where the eye is maximally open. Normally a bit synchronizer would figure that out for you. But here, it's fun and it's necessary to have to set that value. So the eye pattern plot generally helps me, and in this case, I already have this figured out. I've skewed the data in my eye pattern plot. If you remember, its arguments are the input signal, the real part of it, and then L here is equal to the display length, which I think I have fixed to be 2 times ns. Somewhere up in here I had it defined. I could redefine it though. And then the last argument is just how many, oh wait a minute, I was looking at the wrong thing. 32, so it's 2 times ns, and then this is just some tuning parameter, and I made it just a multiple of ns. So usually I'll use it to kind of center the eye, but in this case, because it is a multiple of ns, I know that this is going to be the timing parameter approximately, because it's saying that the maximum eye opening is about 15 samples in to the bit period. It's going to vary with filtering, and it's going to definitely vary for your problem a lot, because you've got that first order like this picture shows, and you look at this and you're saying, is it going to be 15 or not? And you might want to just mess around with that. Turns out with no noise, that is, what the eye pattern looks like. And so when noise is present, all it's going to do is add variance to that, but still the maximum eye opening should be still at 15. You can play with that a little bit. You can do an experiment where you set it 1 sample less, 1 sample more, just to see how that works.
So you compute bit error based on that number, right? That's where your function samples the bit?
Yeah.
Okay.
And when you put that number in there, what it means always, and you can study it in the code, or we can just look at it in the code. I want you to understand how the code works, because I end up having to do this a lot, and I frequently will just kind of start from scratch if I'm trying to get my feet back on the ground. But here is where I'm going through the decision logic. And so what I do is I take a hard decision, so I'm using the signum function to make a hard decision on the value, whether it's positive or negative. Then you can see within Python's indices, the way Python works, unlike MATLAB, first thing is the start index, second one is the ending index, and if it's blank, like it is here, it just means go as far as you can go. The third argument is the stride factor, or the step. MATLAB has those last two turned around. So you put 15, or 16 would go in the middle. But
So it's making an array.
Pardon me?
So it's making an array.
Yeah, it's making an array. So it's taking all the values in the waveform and it's sampling, starting at the timing value, or 15, and then it's going to step 16 onto that, 16 more onto that, and it's going to go all the way to the end, as many as it can get. That sound good? For MATLAB, it'd be very similar. It's just slightly different notation, but that's the decision logic. And then the error detecting is just going into the function that you could explore. We talked about earlier, the bit errors function from digital comm module is doing a correlation between the reference bits, which come out of the modulator data, are the reference bits that come out of this modulator. They're the exact random bit pattern. So that goes in here, and then the estimated bits are in here, and then it does a correlation, finds the maximum peak. And it will screw up if you take the signal-to-noise ratio down really low. It will make so many errors that the ability for that algorithm to find that alignment properly, it will just sort of give up. It might give, I think it gives like 0.5 is the error probability, which is probably just, I think, a number I have to put in there if it can't find it. It's like to say, there's lots of errors in here. It's a coin flip at this point. But in reality, it could be something worse than that when we get into some other schemes like high order modulation. A coin flip is actually worse than 0.5. It's above that line, if I remember right. So just be careful about that, but you're not going to drive it to a really tiny EV over N naught probably, because it's just going to be lots and lots of errors. So with that said, I can just go down here and play with this. So here I have it set for 20 dB EV over N naught. I'm only running 1,000 through, so there's no bit errors, and error probability estimate is 0, but of course that's just because there's no errors, right? The goal, and I think I mentioned this in the problem, is you want to get 100 errors. So you want to run enough bits through. Later on, what I do, and you can add this if you want to, I put a while loop, effectively a while loop in there, so it just keeps looping and generates some more data until you can get greater than or equal to 100. That becomes a better way to go if you're going to let it run for a while and go away, and then it can just generate all the points for the curve. But I'm pretty stingy. When I say stingy, what I mean is I don't like to just set a simulation off unless I'm really confident about it to run all my data points, because frequently it will have an issue unless it's really well tested. And so if you go to bed at night and you haven't well tested it and you say, when I wake up in the morning, my computer will have all the answers I was looking for, it may have got hung up on something. Have you ever had that happen?
Yeah.
I have a lot. So I think it's better to just start with it kind of being manual and then decide what your comfort factor is. But I'm pretty sure I have a setup for automating it later on. Why do I say this? Because I've done so much of this in my life. My PhD dissertation had things with Viterbi algorithms in them that had to run for days over a number of points. This was on a mainframe computer, and I would have jobs. In the days of the mainframe, you would submit what's called a job from your terminal, and then it would go run on the machine, and you could go check the status of your job and see where it's at in the queue and if it's running yet or all that stuff. But since I'm old, I went through that and I learned my lessons. You know, a job would be in there for a week and then I'd end up that it crashed and I got essentially no data out of it. So I learned to be careful. On a PC, yeah, if you're tired, you want to go to bed, and you just want to be a risk taker, just start it running and hopefully you'll get something. But so yeah, another word of wisdom in that area is have it logged to a file. So if it is progressively going up to from a low EV over N naught to a higher value where it's going to have to crank longer to generate 100 or more errors, every time a value comes out, log it to a file or something. So that way, at least if it dies somewhere, you'll have a partial set of values. Do not ever, though, in my view, just say, I'm going to run the curve again. All I want is 1 point down here on the way on the waterfall. I'll just start it all over again. That's very wasteful. So you'll have it, and then you just run one more point. You know, just don't do that. I don't think. I grew up having to struggle to get data, to get points from simulations like this, and I don't just casually say, I'll run all the points again, because I'm like, if they're good already, no, I'm going to keep those values. So I'll probably show you some other techniques that I use to just save the data. I mean, it's really easy in a Jupyter notebook to just take an array that you're just going to start putting values in manually and just save it. You can archive it and other things like that. So you don't have to start over again. And usually when I've done presentations or something to a group of, in the research group I had here when I was younger with another faculty member, kind of like what Dr. Semiari probably does, you have a group meeting, right? So when we'd have group meetings, the students and the faculty would take turns presenting their work, what they're doing, and where they're at in their project. So sometimes I'd put out an error probability curve, and I'd say, there's a couple more points that are still running on the computer. I don't have them yet. They would eventually get added when the paper was submitted or something, but for the presentation that week, I just didn't have all those numbers out of the computer. That's fair also. Because you want to get feedback, right? That's one of the reasons why your group probably does some presentations. Am I thinking about right or not? I don't know how Dr. Semiari does it. I just know how I used to do it.
For meeting?
Yeah, for meetings.
Yeah, we have a meeting on Teams.
Yeah,
Yeah,
you do it on Teams?
yeah.
Okay, it used to be we do it in a conference room, but yeah, the same idea though. You can share your screen and then you can show what you've been doing. Yeah, exactly. So, at any rate, so here's what the Butterworth filter does to a rectangular pulse. It's messing it up. And in this case, I don't know what the optimum is. Like if I make the filter's bandwidth bigger, like 1.0, this is its 3 dB bandwidth. Look at the iPattern plot. It doesn't have quite as much delay in it anymore, and it's a little bit more open. But the problem is, when I add noise to it, it's not going to be the near optimum filter. It's, in no way is it ever the matched filter, because the matched filter we know is the rectangle impulse response. This is just sort of to experiment with that a little bit. So take this back to where I had it, since that was giving me 15. And then when I rerun this, it'll be more or less centered. I guess a good question would be, why does the lag through the filter, especially since this is an IIR filter, why is it changing when I change the cutoff frequency? This is more of a pure signals and systems question. There's group delay, right?
I think they say doesn't the filter essentially needs to be longer if you have a smaller cutoff, right?
Yeah, in this case, though, this filter, this third order Butterworth is just a fixed number, a fixed ratio of polynomials, but it's an IIR filter. So IIR filters typically have non-constant group delay.
Right.
And it changes with, the group delay has got some shape to it. For Butterworth, it generally starts kind of flat, then when you get up near the cutoff, it peaks up, and then it drops back down again. But where that cutoff sits relative to the bit rate, so this is 0.8, the bit rate, it imparts a certain amount of mean group delay that manifests itself into what we're seeing in the iPattern. I mean, we're seeing its opening is shifting. So when the cutoff frequency got bigger, that group delay peak moved out further, and the way it impacted the waveform, it was giving it less group delay. So it's just the timing is showing up differently. It's significant, though, that if you change the filter cutoff during the simulation and didn't redo the timing, you'd get really bad results, because a bit synchronizer at the receiver is always going to come along and get the optimum synchronization point. Okay, so this is run, and then I can explore with the scatter plot down here. Here I'm just sampling from the timing instant across the waveform, but I'm doing this in the complex plane now, so I can see what the points are. And this is pretty reasonable to look at. If I was to take this down to, say, 10 and time on 10, my eyeball just says that's a little bit worse than 15. But usually, to get a better idea, well, it just kind of depends. In all cases, I'd say that doesn't look really very good. It's because there's a lot of intersymbol interference introduced into this because of the filter not being matched. And you can just see at the eye opening, the bundle of waveform values is very fat, which is not good. A lot of reasons for that. It could be a channel distortion that you can't manage. And this actually is leading up to our equalizers, because the equalizer can come along and fix this tremendously, the adaptive equalizers that we'll be looking at. But then you have another side effect that we'll get into. So you can play with the timing adjustment, and if you want to get another flavor for it, you could drop this down like I did over here to 10 dB. And then look at the eye pattern plot. You'll see with all the noise in there, it's definitely getting more closed. Here's our optimum timing instant, and now we'll more clearly be able to see the impact of the noise in combination with the timing. So I go to 10, much worse, right? We can see now we have points that are landing in the neighborhood of the decision region and just about ready to cross the line. We know we haven't crossed the line yet because there aren't any error events. Suppose I jack this up to 10,000 bits through. Now I'm starting to see a few errors, right? And if I went to the scatter plot, I wouldn't do the eye pattern plot with 10,000. Just don't do that because it's too many traces to plot out. But the scatter plot's a lot less work to do, so it'll still take a while. There it's really showing you what the Gaussian noise is doing. Another thing to bear in mind when you're doing scatter plots, and if you decide to put a lot of points in them, Jupyter will house all these in the notebook. This is a SVG graphic, but when you start putting graphics that have a lot of values in them into Typora, export them out, the file gets really big, and at some point Typora just says, I can't do that with that large a graphic, but I haven't had a problem with this part of it. My students in DSP were doing things with WAV files, and they were getting stored in the notebook, and they were having like 30 megs in their files, and then they tried to import them into Typora, and it said can't do it. And I said it's because your notebook is saving all this stuff that there's options of what you can have it archived for you. So just kind of be aware of that. You can see it in the size of your notebook if it's getting big or not. So this is at 10, and then I change this back to 15. And now it's better. However, this measurement over here with 4 errors was done with 15. If I was to take this down to 10, then the errors are getting worse with not the optimum timing. So these are just some things that I think are good to get familiar with. This is the hands-on part of the digital comm. So that'll help you play around in that problem. This exam problem is really an exercise in just getting used to the idea of doing a Monte Carlo simulation, as it's known, and just kind of get the look and feel of it so you become more adept at tuning things and just knowing what makes it work and doesn't work. I'm a fanatic about it. Dr. Semiari, for example, if you're working at a higher level in the systems domain, you don't typically go down and want to play around with all these things, but I've been involved with modem development a lot, so this is where the action's at. But it's all subjective, to where you're at in your stack of things that you might be doing. Okay, so no more questions, just carry on, and I'd like to have it by the end of the week. I'm going to put out another regular assignment here in a few days. But so if you could have it, I think I originally said.
You said it was due next Monday.
Yeah, well.
I prefer that if possible, but I can try to get it in before the weekend.
Yeah, that's fine. We'll go with that. I'm just going to put out something else to keep you going. So.
Okay.
but that's fine. I'm behind. I've got a more challenging week for a variety of reasons. I'm not going to be around. I'm going to be working from home end of the week because finally some contractors are going to be showing up. This is the 5th go at trying to get something installed in our house, some new doors. It's just been not a disaster, but they promised, and then they'd call me. They'll call me later today, and they'd say, "We got an issue. You can't show up today." And I've insisted upon certain days. And then last week, the guy was supposed to come, but the beginning of last week, the guy that was going to do the work had COVID, and the company policy is he needs to quarantine and not come back to work until he's clear. I was happy for that. I didn't want him coming to my house if he was sick. So hopefully he's going to be good to go finally at try number 5. When you're a homeowner and you want to have work done, you're kind of at the mercy of the contractor to get who's going to come and do something for you. You can probably understand that if your toilet was plugged and you needed to have a plumber, you'd probably demand better service, but then you'd have to pay to get that quick service done. Okay, so what we were doing last time, we were starting to look at pulse shaping, and we went through the discussion here. Then we got into the zero ISI pulse shape, which is based on an ideal sync function for the end-to-end impulse response, which would have 0 crossings, but the modification was the raised cosine, which you can see has the sync included in it, but you get to control how much bandwidth the signal is going to occupy. So the sync function would be the dark rectangle around the outside. And the excess bandwidth factor controls how much outside of that window. Remember, the core bandwidth is the bit rate bandwidth, or symbol rate bandwidth in an emery case. So then as you increase the excess bandwidth factor beta, or in my software alpha, from 0 up to 1, then the bandwidth expands by a factor of 2. It's still not nearly as bad spectrally as the rectangle pulse would be, because that has the sync function in the frequency domain, the sync squared in the power spectral density, which has very large side lobes. This is still a lot more bandwidth constrained than that, but of course, an issue with this pulse shaping, raised cosine, based on the sync is that it's a non-causal impulse response, so you have to shift it to the right and then cut the ends off to make it causal and realizable. And that introduces some side lobes that regrow because of the truncation. But it also introduces latency, as we saw last week too. Like if we were choosing plus and minus 6 symbols either side of the center of the impulse response for the raised cosine, that means the mean delay going through that filter is 6 symbols or 6 bits in waveform time. Acceptable trade-off to have bandwidth efficiency in virtually all digital communications, waveform types used commercially. It's what's done. We have to play well with others. We have to conserve spectrum. Even in 5G, I guess in 6G, you still want to use spectrum efficiently. So the zero intersymbol interference criteria is what Nyquist came up with, and he was a Bell Labs engineer. So I showed some examples in Python, this in the notes. If I had time, I'd change this out and put it in Python, but just haven't done it. This is what the spectrum looks like. We looked at this last time. I drew on it, but then I closed it and deleted my saves. So then we get into how do we do a zero ISI system with pulse shaping, and how do we design the filters in the system. So Dr. Ziemer in the book, this is the block diagram he puts up there, and he says we're going to use a transmit filter which shapes the impulse train modulation This is the term that people use, impulse train modulation. So you take and encode your source bits with an upsampler usually, and you just have an impulse train then in the discrete time domain, so it fires once per symbol or once per bit. And then when that goes into the pulse shaping filter, it reproduces from the convolution theorem, right? It reproduces that pulse shape at whatever amplitude value you're going to send from that instant. And that goes out from the transmitter, and it may be complex, like it will be in the next chapter with Emery modulation. But it goes out, and then the possibility of channel filtering exists for a variety of reasons. The channel filter is kind of can be a catch-all. We could view it as something that's actually in the transmitter beyond the pulse shaping filter, but I guess it's probably safer to say the transmit filter, would it contain some sort of pulse shape filter? It might also contain a band limiting filter because of some requirements in the system architecture, like a high power amplifier. You have to do something to suppress harmonics or something like that in the transmitter, so that will add some additional filtering. And the channel filter would be due to the channel model, multipaths, some sort of dispersion that's in the channel. And then the receiver has a filter after the additive Gaussian noise comes in from the electronics front end, setting the noise floor just like in the exam question with the Ethernet. And that is nominally just the desired pulse shape filter, which would be the match filter, but that could also incorporate another filter that just has to be there in the system, an IF filter, or just something that's needed in the DSP front end, digital downsampling type of things that might be done. Generally, though, you try to keep those extra filters at a bandwidth that's far enough away from the match filter and the pulse shape filter at the transmitter to not interfere, but if they do impart some additional filtering action, then maybe that's where the equalizer would be needed, or you have some inverse filter somewhere, because the top of this section says 0 ISI, and 0 ISI would mean that nominally no intersymbol interference at the sample values over here. But that's hard to maintain perfectly, so you're just trying to get it to be minimal.